My name is Denis Gundarev. I work at VMware as product research engineer. And this presentation is just my own opinion. It's not related to my employer. It's not something that you should follow or should use. But it's I will tell you, I will describe you how to describe PKI to your boss, to your mom, to everyone, or to your security department. I'm really glad to see you in this room specifically, because it looks like you actually trust encrypted information, the information that was transferred over the encrypted channel. Because if you try to get to this session, you probably seen the schedule in front of the door, and there's same session, which is actually my session, at the same time in two different rooms. But I see you in this room, and it looks like you are in the correct room because nobody is like jumping and not trying to get to another room. And I hope that's because you got the location of this session from the website, NGINX conference website that has a schedule. You can see it. And of course, it's secured. It's protected with transport level security, encryption. And it looks like it's information that you can and should trust because it comes from the website of NGINX Software Incorporated. So again, I'm glad to see you here. And this presentation would be mostly like basics, introduction to the public key infrastructure, how it's used in different environments, how it can be used, and how it actually works. Because what I found when I was talking with different customers, with different vendors, many people don't really understand how it works. They think PKI is a very complicated infrastructure, and you need to have a security certification that costs you money to be able to understand it, or you need to be a cryptography guru or something like that. No, it's much easier. You need to understand basics. How does it work? Everything is based on the trust. And in PKI infrastructure, everything is based on the trust. Different entities, different objects, computers, software applications, people trust each other based on the information that they got from opposite side. This opposite side, in most cases, presenting you a certificate. So if you are a Windows user, you've probably seen this window. Most probably you're not a Windows user, but it doesn't matter. Every certificate can be presented in the UI, can be shown using OpenSSL command. But every certificate, no matter where you look at the information about the certificate, it has some information, such as name of the person who had this certificate, or web server who has the certificate, the issuer of the certificate, some other fields. And in my opinion, it's very similar to driver's license. The certificate itself is a document that has name of the person or name of the web server that this certificate is issued to. It has the entity that issued this certificate or the license. In case of driver's license, it's the state of California who issued this driver's license. It has a validity date, because you can't drive with expired driver's license. You can't drink without the valid driver's license. And you shouldn't be able to read the contents of the website with expired certificate. It means basically that this website doesn't have a right to show you the information if the certificate is expired. The certificate in the same way like the driver's license have intended use. Describe it on the certificate itself, or in case of driver's license, I can drive only just regular cars. I can't drive the bike. In case of this certificate can be used only to sign the email that I send into someone else. It's not intended to be used as a web certificate, as a certificate for the web server. The difference between the license and the driver's license and the certificate, that when I have the certificate, I have a private and a public key that also is a part of the certificate. It's a part of the certificate. Technically, you can issue the certificate without public key and without the private key, but it would be just useless. So who is issuing the certificates? The certificates are issued by the certification authority. What is certification authority? Certification authority is some legal entity, in most cases, that has a root certificate and some entity that is trusted by some other entities. And in case of driver's licenses, we can assume that the root certification authority in the US is the federal government. That federal government is not issuing the driver's license. Federal government can issue some other forms of identification, but the most common form of identification in the United States is a driver's license, and it is issued by the states. And I think in all of the cases, it is issued by DMV. So in terms of PKI, the federal government is the root certification authority. And the states are subordinate certification authorities or issuing certification authorities. It's actually the entities that store the database of the certificates that were issued to the people, or driver's licenses in this case. So root certification authority grants permission to subordinate certification authorities to issue the certificates or driver's licenses in this case. What you can do next with this driver's license? You can go to the bar, or you can go to the airport to try to get on the plane. And some guy will verify your driver's license. This guy is validation authority. He is checking that your certificate is well formed and that it has all the valid attributes, that that your driver's license is not expired, and if it's not expired, if it looks legit, he will let you in. But if it's not, or he has a doubt that maybe it's not a real, it's a fake ID, what he will do, he will take you with your driver's license to a separate room where he will check your driver's license across the online database, that your driver's license is actually valid, that it was issued by the state, it has these attributes, and it's valid. So before presenting this driver's license, what you should do first, you should verify his ID or his badge, that it's not just random person asking you for a certificate. It's an officer that has a right to do that, and in the same way with like with driver's license, you can check his badge, check his badge number, call if we're talking about the police, you call the police department and ask, is this police officer working in this police department? Is his badge valid and not stolen? So you can always verify. So validation authority can be something on the server side or on the client side. In most cases, if we're talking about web use cases, when certificates are used for to secure traffic between the web server and the client. In most of those cases, the validation authority would be the end user, and more specifically, end user browser. So it's a responsibility of the browser to verify that certificate has the correct checksums, that it's not expired, and if browser doesn't care, then you can get into trouble. I mean, user can get into trouble. So that's the reason why, if we're talking about secure browsing, it's better to have web browsers that were installed from the trusted sources, that the Internet Explorer or Firefox is not modified or not hacked in any way. So validation of the certificate or driver's license is very important, but it's very difficult. As example, there's a lot of ways, a lot of different IDs in real life. There's a lot of different IDs issued by the government. Some of them might be old and has less protection, and people can use those fake IDs to try to get to the plane or try to get a job. So in case of the job in the US, there is a government system that let you as employer check the validity of the license or the social security number of the person by checking it online, and it's called E-Verify. But in this, if we come back to the certificates and the PKI infrastructure, I would call it Online Certificate Status Protocol. OCSP is a protocol that can be used within your PKI infrastructure to verify the validity of the certificate. Because if we have a certificate that was issued by mistake, somebody requested a certificate for a web server, and he requested it because he got root access to the web server and put the required web page or modified DNS, or in some way or another tricked the certification authority, and they issued the certificate. After certification authority found that it was a fraud, certification authority can revoke this certificate. And usually, most of the certification authorities, they publish list of revoked certificates on the scheduled basis, and the client should usually do the same. On the scheduled basis, download the certificate revocation lists and verify it. But in 2017, we have certification authorities that issue certificates for free. We have massive implementation of certificates in the web. And if we will force clients to download certification revocation lists on the scheduled basis, this scheduled basis should have so small interval. And even it would be like if client would try to download certificate revocation list every second, it's still not enough. Can happen that certificate would be issued, then revoked, and some of the users will still trust it. So to protect from this, there's additional standard was implemented and designed called Online Certification Status Protocol. It's a web server that is hosted on the Certification Authority platform that responds using API for the requests to verify that certificate is valid or not. That's how it works. Now, that's PKI. That's how the certificates, similar to driver's licenses, how they issue it. But now let's switch to the encryption. So what is encryption? What is good encryption? What is bad encryption? Good encryption is encryption that you can decrypt, because otherwise it's completely useless. You can just throw data somewhere else, and that's it. So in general, there are two types of encryption, especially when we talk about transport level security, the security of the data sent over the wire, not the data that is stored on the disk, but the data sent over the wire. There are two most commonly used encryption algorithms. One of them is symmetric encryption. So how does it work? Let's assume that we have two guys. One is stereotypical Russian, another one is stereotypical American, and they trying to talk. They need to talk, and they trying to exchange information in a secure fashion. So when you catch their encrypted conversation, it looks unreadable. You don't know what is that. You see some characters, but it doesn't mean anything for you. In the symmetric encryption, it's like conversation, or you already got the conversation in the middle of the conversation. So if you got the conversation in the middle, you can't really get what they are saying. But if you will start listening for their conversation from the very beginning, before they establish the session, you will see some weird stuff. You will see that one of the guys, in case of protocols, it would be a client, is sending the message to the server, like, hey, I want to encrypt all the communications between us, but here is my encryption key. Please use it to encrypt information for me. And it's a symmetric encryption. That's how it works. The server side get this encryption key, and then they exchange the information, and they able to encrypt and decrypt this information live in real time, pretty fast. Data is encrypted. But if you got the beginning of the conversation, you know what is happening, what they're talking about, and you can decrypt the whole contents of the conversation. So symmetric encryption is fast. But it's basically obfuscation, because it's really easy to intercept the private key, the secret key, and decrypt the information. So how to beat this? There is a symmetric encryption. So how does it work? Asymmetric encryption is starting with the client that trying to talk to the server, and server, during the negotiation or handshake, gives the client the public key that can be only used for encrypting the data, but not for the decrypting the data. It's like an envelope that can be closed by everyone by open it, but it can be opened only by the server. So with asymmetric encryption, the client asks server that I want to use asymmetric encryption. Server responds with the public key, and then client starts using the public key to encrypt the data and send it to the server. And the server, because it has a private key that can be used to decrypt the data, it decrypts the data and reads it, and everything's fine. So everything's fine. You can't get the information. You can be very sad if you are working for government and you got the TLS data between the clients. But many people think that TLS or SSL, it's very costly. It's heavy, and it's using a lot of CPU cycles, and your web servers will become slow if you will implement SSL and TLS. And many customers, many people, many companies they are implementing SSL or TLS only on the front end, and they never use it on the back end because they want to increase the capacity of the backend servers, and they don't want to use encryption because they think this asymmetric encryption is very heavy. But the common misconception here that asymmetric encryption is used in TLS only for establishing the session. Asymmetric encryption is not used to encrypt the data itself. That's how it works. So, same two guys trying to establish the TLS session. SSL, TLS, I use both of these words interchangeably, but it basically, I don't want to go into the details. What's the difference between SSL and TLS? SSL is an older version of TLS, or TLS is a newer version of SSL. It's a protocols that use it to establish the connection, to perform the handshake. And the different versions of the TLS or different versions of SSL, they have different sub-steps, verifications of each step. They may use different ciphers, but generally, SSL and TLS, just for understanding how it works, it doesn't matter, SSL or TLS. Basically, it's the same. So how the TLS handshake works? The client trying to talk to the server, and if we talking about normal TLS connection, the client usually use a function called server name identification to present to the server the name of the server the client wants to talk with. So the client saying, hello, I can speak different ciphers or different languages. I support TLS 1.0, I support TLS 1.1, I support TLS 1.2. In this case, it's different languages, Russian, Spanish, English, Chinese. And clients say, I want to talk to, I don't know, google.com. And the client also generates a small random number and send this information as a client hello package to the server. Server get this package, verifies that this is actually a package that is intended to be delivered to this server. So we have the correct name of the server. And server select the strongest protocol that that server supports and respond to the client that, okay, I support TLS 1.2, or in this case, Yosemite Sam says, I speak Spanish. And it sends the private key, it sends the public encryption key to the client. And this code is called server hello message. Next thing that client is doing, the client is verifying the certificate and the public key of the server and decides should it trust the server or not. So it decides, yeah, this guy is from California, it has California ID, I know how it looks like. Okay, let's proceed with the conversation. Then client encrypts the combination of the two keys, client key and the server key, encrypts it with the server public key, and send this information to the server. Server decrypts this information and compares the random keys that were generated by the server and by the client, and if server is able to decrypt, and if the information, if the random numbers are valid, server confirms the connection, and they start, they negotiating the ciphers to use over the wire, to use the symmetric encryption. So after the keys are exchanged, we have one encryption key that is that this encryption key was never sent in a clear text or basically obfuscated over the wire. It was sent encrypted by the public key of the server, and the client knows it because it generated part of this key. Server knows it because it was able to decrypt it with the private key. Now we have a secret key that we can use for symmetric encryption, which is fast. And now we can talk. So after the key message here, that after the TLS handshake is established, the server and the client, they are using symmetric encryption. They are not using asymmetric encryption, which is costly and very resource intensive. And basically, what does it mean? That if you are not letting your web servers establish many TCP connections, many SSL connections, basically if you have something in front of your web server that can do SSL offloading, it means that only your front end is getting the load of establishing TCP connection. And if this front end is well designed, it will do this very fast. So the key thing here in this conversation between client and server is the fact that client, before proceeding with sending some sensitive information, client checked the validity of the certificate of the server, or in this case, it's checked the driver's license of the server. And it trusts, the client trusts the web server and the entity that issued the legal entity that issued the certificate. But who do you trust? I have an example. So when I came to US about 7 years ago, I went to the grocery store to buy some beer. And when I came to the grocery store, the guy, the cashier, said like, "Oh, perfect. I will sell you this beer, but please give me your ID." I gave my ID. What kind of ID I had? I had my Russian passport. And I showed my Russian passport to the guy at the grocery store, and you know what he said? "Sorry, we don't sell beer to Russians." Like, what? But it's easy to understand. He never, this was a young guy who never seen a Russian passport before, and he don't know, is it valid passport, is it passport at all, or what is that? He knows how to check the driver's license, California driver's license, maybe driver's license from some other state, but he never seen the passport, paper passport from Russia, and he said, "Oh, I can't trust the validity of this certificate that you present in me. So I'm not going to establish the connection with you and take your money." Who do you trust? If you're using Windows, which is probably not the case, you trust those guys. If you think it's funny, you can open your Mac and check the trusted certificates, or check your Mozilla trusted certificate root. You trust some guys that has weird names, like, and I'm not going to name them because they might be here. You may trust some companies that you never heard about. You may trust Japanese government. Why? I don't know. You may trust some other governments because those root certificates are in the trusted certificate authorities list that is built in with operating system or with your browser. But who do you trust? Do you really trust Symantec? Do you really trust Komodo? Do you really trust some other guys? I don't know. According to the Reader's Digest, the most trusted person in the US is Tom Hanks. The second trusted person is Sandra Bullock. Do they issue certificates? No. Who is issuing certificates? Symantec, DigiCert, other guys. Should you trust them? I don't know. You probably should. But there is one person in the world that you should really trust. Trust yourself. When you build in the infrastructure, internal infrastructure, like backend infrastructure for your web services, it is always good practice to use encrypted traffic between different servers. Because if somebody will break into your environment, it is better to have communications between servers encrypted. Even if your backend inside your environment. Should you buy the certificates from those guys? If you have money, you can, but you can save money by deploying your private certification authority that would be used inside your organization. Many customers, many companies think that, oh, self-signing certificates is not secure. I should use certificates from the trusted certification authority, like DigiCert. Yes and no. The certificates, the root certificates are secure if you hide your private key for the root certification authority. For the root certification authority or subordinate certification authority that is actually issuing the certificates. If this key is hidden and nobody can use it, you control this key, you would be probably more secure than if you will use certificate from someone who may fail during their maintenance operations and revoke their own certificate, or some other company that for testing purposes can issue certificate for the host name called google.com just for testing purposes. If you use your private key, you should keep it secure and you will be fine. How to keep it secure? The basic stuff and cheap stuff. Keep the private key protected by ACLs. It's not very solid practice. The best practice would be to use hardware security modules. With hardware security modules, what is hardware security module? I have a small slide deck from Amazon. They have a product called Cloud HSM, which is basically implementation of the hardware security modules running somewhere at Amazon data center. You can build a cluster of these hardware security modules, and you can distribute the private keys. You can store the private keys on the hardware appliances where you physically cannot get the private key from this appliance. You can you can send the command to the hardware device to generate the private key, but you can't get this private key out of the device. So you basically cannot steal the issuing certificate. You can generate certificates. You can do whatever you usually do with your OpenSSL command line, but you can't get the private key in the file. It sounds pretty simple, but it's simple and stable hardware security modules is the best solution to protect your private keys. And after you implemented it, you can use it with different applications. You can use it with your backend databases. And of course, you can use it with NGINX if you just modify the configuration of your in your NGINX conf and specify the engine for your HSM device, OpenSSL agent for HSM device. NGINX do support this, and it should work. Ask your friends at NGINX how to actually implement it. Because unfortunately, I haven't found the actual implementation guide from NGINX how to implement this. But it's basically easy. You, instead of the path to the private key in the NGINX conf, instead of typing /etc/ super secret private key .pki, you type engine column Cloud HSM or Gemalto HSM or whatever OpenSSL engine you have installed on your web server, and then the identifier of the key. That's it. NGINX will be able to get the certificate, the public key for this certificate, and when NGINX will need the private key for decryption, it will use the OpenSSL engine to talk to the HSM to decrypt the message from the client. So again, I would recommend you to implement your own private keys, your own PKI infrastructure, and use it for everything internally. I came from the Windows side of the world, and everybody is using it there. With Active Directory certificate authorities, works fine, works perfect. Communication between clients and servers are secured, managed. You can do this on every platform, and it's usually easy. We have just a few minutes left, and I will try to run with the rest of my slides. But basically, when I'm talking about trust, trust is the core feature, core requirement when you implement PKI. Because if you don't trust something, or if you trust someone who you shouldn't trust, you probably will get into trouble. Probably you don't see on the screen, but here is the website of DigiCert certificate. Very popular, very good certificate authority, and the URL shows that the website, the connection to the website is secure, but on the right side, it actually shows the connection is valid, is using the valid certificate, but the name of the certificate of issuing of authority do not trust Fiddler root. So if you use tools like Fiddler or Meeting Proxy or don't remember the name of the tool on the Mac, you easily implement in-the-middle attack on your laptop. This can be done by every hosting provider. This can be done by almost anyone who controls the wire. They can implement man-in-the-middle attack if they have a certificate, the certification authority that if they have certificate from certification authority which is trusted by your browser. In case of Fiddler, I personally installed the fake root certification authority into the list of trusted roots on my computer, and now I trust everything that is dynamically generated by this tool called Fiddler. It works the same with Meeting Proxy and other stuff. How to protect from this? Do not trust fake certification authorities. Do not, if you as example, like you're trying to troubleshoot something, you're trying to verify this, and you trying to install tools like Fiddler or Meetum proxy on your web server during the troubleshooting, most probably your root certification authority on the Meetum proxy would be just stored in the file, and everyone can steal it and use it in some unintended way. How to protect? First of all, do not trust sales guys from certification authorities. When they say that extended validation certificate is more secure, they say something that's not related to the truth. Because extended validation authorities, extended validation certificate is just a certificate that ensures that certification authority did their job verifying who asked for the certificate. They do an extended verification, which should be basic verification. When you request a certificate for your web server, if you request a basic certificate, not extended validation, they ask you to modify your DNS records. They ask you to respond to the email message sent to the root at website.com or something like that. They often even don't talk to you over the phone. And of course, they don't verify that you legally have a right to own this domain. With extended validation, they ask your ID. They verify that you are the person that is that has a right to sign the papers for the company that owns this domain, and such information like that. In the result, the only thing that changes is the way how the certificate is presented on the client. You see the green bar in the browser. That's it. Encryption algorithms are the same. The validation of the certificate, the certificate needs to be validated against OCSP and serial. Everything is the same. HTTP strict transport security is a way to enforce the client to talk HTTPS only. It's not like redirect from HTTP to HTTPS. It's the way to enforce the client, the browser. But if your client doesn't care about the headers or doesn't support HTTPS strict security, it means nothing. You will not enforce it. So you have to enforce it by basically disable HTTP. HTTP public key pinning can be a good option, but it is easily can be replaced because HTTP public key pinning is an option that you can configure on your web server to send the hash of the public keys of the certificates in the chain to enforce the client to check that certificates are specifically the same as they should be, that they are not replaced. But again, if client doesn't care, then this function doesn't work. DNS certification authority authorization. It sounds like a way to enforce certification authorities to follow some rules, basically by checking additional settings that admin configured. So it's not real protection. OCSP stapling is the way to send OCSP response from the OCSP server together with the certificate. Good enough, but again, it should be supported and not ignored by the client. And by the client, I usually say, I usually talk about the browser, but it can be your web components that are talking to each other, your backend server, your backend web server talking to the database, and other stuff like that. So this presentation would be available, and you will be able to get those links, or you can try to memorize them. And I think that's basically it. That's what I have for now.